I'm going to continue to look at the graph of the sine function, and in this video we only have one transformation really left to look at, and that is the phase shift. Whereas if we recall, when we had the graph of something like y equals x squared, if we had y equals x minus 2 quantity squared on the inside, remember I mentioned here this would be the graph of your parabola, but then the minus 2, if there's a minus 2, that's going to cause the graph to go 2 units to the right. So when we think of that happening with our trig function, we refer to that as a phase shift. And if we go and look at our y equals a sine of bx minus c plus d, we've talked about each one of these so far. We've talked about A deals with the amplitude, the absolute value of A is the amplitude, and the coefficient B, the coefficient of x, B here, helps us to calculate the period, and D we said was telling us whether the graph was going to move up or down. If it's positive, it goes up. If it's negative, it goes down. Now we want to look at what effect is this whole bx minus c having on the graph, and that's going to cause what's referred to as our phase shift, and that's going to start moving the graph to the left or to the right. So if we look at an example here, we will look at y equals the sine, and we're going to look at x minus pi over 2. So if we look at the graph of this function, we can type in y equals the sine of x minus pi divided by 2, close the parentheses, and I'm going to go to zoom 7, which is zoom trig, and we have our graph. And at first it looks like there's not really a whole lot of difference here, but if we look closely, the graph has moved. So if we copy this, we'll bring this over and compare it to the sine function. And once again, let me go over here. And if I was to go to y equals, just to see the difference, if I was to type in now the sine of x, and watch when I hit graph here, you're going to see the sine function be graphed out, and we can kind of see what effect this pi over 2 is having. So here's the sine function here. So if we start here at the origin, this is the original sine function right here. And we can see now that this point from the origin has actually been moved over. So what's happened here, this graph has been moved over pi over 2 units, because this location right here, this point is pi over 2. So the origin where this graph sine function normally starts has now been moved to here like this. So we can see that this is caused what we refer to as a phase shift, where the sine function, the graph has been moved pi over 2 units to the right. So let me go ahead and just look at the sine function by itself. So we can see again, the sine function normally starts on the x-axis at the origin. And you're going to see why here in a little bit why that's important to be aware of. So here we have, this is just the plain sine function. So notice where the graph starts here, it would normally go up and around, up and over here, and that would represent from 0 to 2 pi. So what we're going to notice here, though, this point has been moved over to here. Whoops, not that far. I'm sorry. This point has been moved to here, which is a distance of pi over 2. So now this point would actually correspond to here, and this point is now here. Okay, so once again though, if we go through each of the calculations, let's look at the amplitude. Again, that means we're looking at the A value, so the absolute value of 1 is still equal to 1. So we can see here this distance for the amplitude is still certainly 1. The period was 2 pi over b. B is our coefficient of the x. Well, the coefficient of the x is still 1. So notice we haven't changed the amplitude, we haven't changed the period. So the period here is going, if we start, if we think from this point, we could see here down below from valley to valley, we still have a period of 2 pi. And again, you could also look at the period going from peak to peak. That distance would be a distance of 2 pi. All right, now D, we haven't moved up or down. So the graph has no vertical change. But now we want to look at this bx minus c. And for the bx minus c, in order to find what I refer to as this phase shift, and a little bit later I'll kind of refer to this kind of as our starting point. We're going to take what's inside the parentheses. We're going to take this x minus pi over 2. Okay, that's the bx minus c. And we're going to simply set that equal to 0. And if we solve for x, we get x equals add pi over 2, so we get a positive pi over 2. And what that means is we have this phase shift of pi over 2. So that means where this point was normally at 0, it's now moved over here. We're starting at pi over 2. So we would have pi over 2, pi, 3 pi over 2, and 2 pi, because again we're still starting here at 0. So this graph has a phase shift of pi over 2, where it's gone pi over 2 units to the right. And you can probably guess here, if this x minus pi over 2, if this had been a plus, then it would be pi over 2 units. It would shift to the left. So if we review here a little bit, when we look at y equals a sine of bx minus c plus d. So when we go to calculate the amplitude, it's the absolute value of a. If we calculate the period, it's 2 pi divided by b. And if we look at the phase shift, and sometimes I refer to this as kind of a starting point, and I'll kind of explain what I mean by that, but that's where we're going to take the bx minus c and set that equal to 0. And when I say this is a starting point, it's a starting point to represent one period. And if we were then to take to find the end of a period, now I'm not saying the start of the graph because the graph continues forever, we could take the bx minus c and set it equal to 2 pi. So this would give us one particular starting point and one particular end point to represent one period for the graph. And that's how we could set this up. We have, again, A, absolute value, is the amplitude, the period, 2 pi divided by b, where b is the coefficient of x, and then the phase shift, bx minus c, set that equal to 0. And if we want to know the endpoint then for the period, we could simply set that equal to 2 pi. And in both cases here, you would solve the equation for x. And then, of course, the last part here, D, is basically giving us our vertical shift. And that's going to tell us whether the graph is going to shift up or down on the y-axis. Okay, so hopefully now you feel comfortable with looking at the graph of a sine function. And I'm actually going to look at one here, and we can look at it by hand, and then we'll look at it using the calculator. So if we are given, let's say, y equals 3 sine of 2x plus pi over 4 plus 5. Now, of course, we could enter this into the calculator, but I want to see if we could go through and if we had to graph this by hand and see if we can analyze this to determine the particular shape and how the graph is going to be shifted. Now, what I want to tend to think of when we think of our sine function, we want to think of what does just the plain y equals sine x look like? Well, we said it's going to start here. If we think about starting at the origin, it's going to go up, down, down, and then back up. And we said that would go from 0 to 2 pi. And we have kind of these, if you remember in one video I talked about, we have kind of these 5 key points, and the standard y equals sine x, this would be 0. Then we would have pi over 2, pi, 3 pi over 2, and then we would end up at 2 pi. So, and I would mark off, and I said we would have these steps where this would be one step from between the key points, and this would be a second step. This would be your third step, and then here we would have our fourth step. So it's 1, 2, 3, 4. So I want to kind of think about those steps and see how we can come up with this graph for the 3 sine 2x plus pi over 4 plus 5. So I'm going to start out by first identifying what is the amplitude. Well, the amplitude is going to be the absolute value of 3. So the amplitude is 3. And if we calculate the period is going to be 2 pi divided by b. So in this case, that's going to be the 2. So we end up with the period is equal to pi. And then we want to look at what's called the phase shift, or kind of what I refer to as kind of our starting point for a particular period. And that means we're going to simply take the 2x plus pi over 4 and set that equal to 0. So we would get 2x equals negative pi over 4. So x is equal to, if we divide by 2, we can think of multiplying by a half, so that would be a negative pi over 8. Now, that gives us our phase shift. So in this case, we have a phase shift of negative pi over 8. So that means up here, this graph, where we normally would start here at the origin, it's going to be moved over to the left pi over 8. And every other point as well is going to move pi over 8 to the left. So now I want to look at how we can calculate what I refer to as our steps. And the steps, remember, that I'm referring to would be if we start, then each of these steps here, that 1, 2, 3, 4, we have 4 equal parts or 4 equal steps to this graph. And I want to calculate how big is each step going to be. Well, we know that if the period is equal to pi, then to calculate each individual step, I want to take the period and divide that by 4. So therefore, we're going to have our 4 equal steps. So therefore, I would take the period, which in this case was pi, and divide that by 4. So each step is going to be a distance of pi over 4. Now, I do want to point out our starting point, if we go up here and look, our starting point was negative pi over 8. And to make things easier with fractions, because I know sometimes people tend to not like fractions, but to make this a little bit easier to work with in terms of our fractions, because we have a denominator up here for the starting point to be 8, then I want to change our denominator for the pi over 4 to 8. So if I multiply here by 2 and multiply the top, we're going to end up with 2 pi over 8. So this is what I want to use here for my step, just so that when we add it here to our starting point, we are consistent with having the same denominator, so that it makes it much easier for us to add our fractions together. All right, so now we have our phase shift, our start, our step, and just to make sure that we do this correctly, we can actually calculate where the end point should be for this one period. So we're just looking at graphing one period where start's going to be at negative pi over 8. And then we know we're going to have 4 equal steps. And of course, if we keep adding that 4 times, we would find the endpoint. But to kind of make sure we do that correctly, we can take 2x plus pi over 4, just like we did up here for the start, 2x plus pi over 4. But now, instead of setting that equal to 0, we can set that equal to 2 pi. So if we solve, we would get 2x is equal to 2 pi minus pi over 4. And here, if we're going to subtract this, we need a common denominator. So this would be, what do we need? 4. So that would be 8 pi over 4. So therefore, we would have 2x is equal to 2 pi, or 8 pi over 4 minus pi over 4. We would get 7 pi over 4. And then once again, to get rid of the 2, we could divide by 2 or multiply by 1/2, and we would have 7 pi over 8. So we know that now the beginning of our period that we're going to use is going to start at a negative pi over 8, and it will end at 7 pi over 8. So now, using the information we just found, let's see if we can come up with the graph of this particular function. So let me see here if I can sketch this out. All right, now to start off with, we know that the function is going to go, and let's see, one thing I did leave off at the very end here is we have this plus 5. So this is going to move the entire graph up 5 units. So that's the first thing I do want to mark off. So we're going to go up 5 units. 1, 2, 3, 4. So if we go up 5, let's see, 1, 2, 3, 4, 5, 6. So essentially now our x-axis, as far as the way our graph's going to oscillate here between the two over the x-axis, we can now think of that occurring at y equals 5. So this is kind of our new axis where the graph is going to oscillate something like this. So keep in mind, we said that for the sine function, we actually start the graph here on the axis, and then it normally goes up. So that means that our axis has moved up here, so it looks like our point would start here on the axis, but we need to look at how is it going to be shifted. So we know that our starting point, we set up here, the phase shift, the starting point is at negative pi over 8. So that means if we start at a negative pi over 8, and I'm just going to mark this off here as negative pi over 8. And just so we're consistent, I want to go ahead and mark off some units here on the x-axis. So we have negative pi over 8, and then of course here we would have 0, and then we would have positive pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, and 7 pi over 8. Now, if you've noticed, what I actually did here was using our step. We said each step is going to be 2 pi over 8. So if I was to start at negative pi over 8 and add 2 pi over 8, then that would take me to a positive pi over 8. And then if I add 2 pi over 8, so this is adding 2 pi over 8. So 2 pi over 8 and a negative pi over 8 is pi over 8. And then if we add another 2 pi over 8, that would give us 3 pi. Another 2 pi would be 5 pi over 8. And then we get 7 pi over 8. So here's the 1, 2, 3, 4 equal steps in the graph. So what I've kind of marked off are these 4 steps that we're going to have in the graph as we go from the axis to the peak, then from the peak back down, and then down to the valley and back up to the axis. So knowing that, we know that our function is going to start at negative pi over 8. And I said that the sine function starts on the axis. So that means our starting point would be here on the axis. And then our amplitude was how much? We need to know how high do we go? Well, the amplitude was 3. So that means from the axis, we're going to go up 1, 2, 3. So we're going to go up to the 8. And then we're going to go down 3 units. So we're going to go down 1, 2, 3. So we're going to go all the way down to 2. So here is the top part of the graph, and at 2 we would have the lower part of our graph because our amplitude is 3. So now we know that our first step, starting here, we're going to go all the way here to pi over 8. So that means we're going to curve all the way up to pi over 8, and we're going to go all the way up to the highest peak. And this here would be the first step for our graph. Okay, so that is step 1. And then we know that we're going to go to step 2 down here, 2 pi over 8. So that means that would be 3 pi over 8. And the graph's going to be back down on the axis. And then our next step goes over to 5 pi over 8. And that's going to take us down to our valley. And then our last step here, 7 pi over 8, is going to take us right back up to the axis. So we can see here that we had, this is our first step, second, third, and fourth. And again, that will give you the 1, 2, 3, 4, what they call the 5 key points of the graph. And we now have one complete period. And if you notice, we said before the actual period was pi. And we can verify that because if we started at negative 7 pi over 8 and went to, if we started at negative pi over 8 and went to 7 pi over 8, we could say 7 pi over 8 minus a negative pi over 8. The two negatives would become positive, so 7 pi and 1 pi, that would be 8 pi over 8, which would be equal to a period of 1 pi. So that verifies that everything matches with what we had stated. And even if we look at the 7 pi over 8 as our ending point of the period, we can see that we started at negative 7 pi over 8 and our graph ended at 7 pi over 8. Now when I say start and end, that means the period. Of course we know that this graph would actually continue the same pattern to the far right and then over here to the left. Okay, so now let's look at this on the calculator and see if we did a good job with coming up with the graph. So if we go into y equals, clear out what we have here, we're going to type in our function that we have, and our particular function here was y equals 3 sine 2x plus second pi divided by 4, close the parentheses, and then plus 5. Now let's see, if we look at the way I came up with my x and y axis here, my x-axis is going from negative 7 pi over 8 to negative pi over 8 to a positive 7 pi over 8. So I want to use this for my x minimum and x maximum. And then the y-axis, I'm going to go from 0 to 8. And let's see if we can come up with a similar graph here. So I'm going to go first of all to the window, and we would type in negative pi divided by 8, and the max was 7 pi divided by 8. And the scale, I'm going to leave that, well, let's go ahead, since each our scale, if you notice here, was pi over 8, so let's make the scale here second pi divided pi over 8. And then y minimum, we'll just make 0, and the y maximum will go all the way up to 8. Just so we can see the graph a little better, let's maybe go all the way, let's make it one bigger, so we'll go up to 9. And let's see if we look at the graph, and let's see, what did I do wrong? number 1. Y equals 3 sine 2x plus pi. Okay, when I type this in, this should be 2x plus pi divided by, let me insert 4. So I left out the 4 didn't show up here, so it should be 2x plus pi over 4 plus 5. So now if we go to graph, we can see our graph does start here, goes down, and comes right back up. So that looks very much like the graph we came up with, where we have 1, 2, 3, 4, 5. The graph is starting here at 5. It goes up, down, and right back up. So this is how you can go about graphing a sine function by simply knowing the amplitude, the period, the phase shift, which is kind of a starting point, and then you can mark off the step by simply taking the period and dividing that into 4, because we have 4 equal steps. And just for a way to double check is to calculate the endpoint for the period, which tells us if we keep adding 2 pi over 8 like we did down here at the bottom, if we add 2 pi over 8 4 times, we should end up at 7 pi over 8. And the key thing to remember here is our graph sine function, it starts on the axis and goes up, or it could actually go down. Now, what do you think would cause the graph here to go kind of the reverse way like this? Well, the only thing we would have to change in our function is if we were to actually come along and put a negative in front of this. So let's look and see if that would change the graph here. If I was to go to second, insert a negative sign, notice now if I look at the graph, just by putting a negative sign, the graph goes in the opposite direction. So that's one thing I want you to be aware of. If we put a negative in front, the sine function normally starts and goes up this way, but if we put a negative, it's going to start and go down. So therefore, if that was the case, we would end up with something here that's like the graph in red. It's going to cause it, instead of starting up, it's going to start out going down.